4.2 area. Today we're going to be taking a look at area from a different perspective, and there are connections that we're going to make back to section 1, but it's going to feel a little disconnected at the beginning, and in fact it's probably going to seem like something that maybe you haven't even seen notation like this before. So let's take a look. Sigma notation. That's what we're going to be using. It's a way that we can write a summation of a bunch of things. So the things that we are going to add together are A1, A2, A3, up to AN. So we have a finite number, but we don't know necessarily how many of them there are in general. So it's written as A sub n. The sigma, that capital sigma notation, is a summation symbol that we use in mathematics. The part underneath of it tells you where you start. This says I equal 1. And the part on the top tells you where you end. It ends at n. So the notation on the left and the notation on the right, of course, are the same notation, but it's like we're trying to add up. This, you're probably very comfortable with me writing it like this on the right-hand side, A1, A2, A3, all added together. But we'd like a more condensed way of expressing that, and that's the notation you see on the left. So this is the shorthand. This is the texting language right here, right? It's something that's shorter than we have to write on the right-hand side. So we've condensed it on the right-hand side, but it means the same thing as the left-hand side. Each of these things have sort of vocabulary associated with them. I is called the index of summation. A sub I is called the ith term. The number underneath is called the lower bound. The number on the top, which would be a number in general, is called an upper bound on our summation. So the first thing we're going to do is we're just going to work a little bit with this notation and find a sum. So this example shows it starts at 1 and it ends at 6. And it gives what looks kind of like a formula or an equation. In terms of I, the reason it's in terms of I is because the I is what's written down underneath. I is what we would call like a dummy variable. So you can use any letter there. It doesn't have to be I. But we do see I used frequently. We also see K's, N's, and J's used in that frequently. Why those specifically, I don't really have a good answer for you. They could be anything, but those are the ones that people tend to use. All right, so we're going to find the sum of this, or we're going to find sums in general in a couple of different ways. This one we're going to find sort of directly. And what I mean by that is we're going to actually figure out what is A sub 1, what is A sub 2, and how many of these A guys are we going to need? 6. So we're going to find all of them up to 6. And we're going to use it, or we're going to do that, by taking those subscripts 1 through 6 and evaluating them in for I. So the first one literally is, I'm going to do 3 times 1 minus 2. And what is 3 times 1 minus 2? It's 1. Then we go to the next one. Now I'm going to do 3 times 2 minus 2. It's 4. We're going to do 3 times 3 minus 2. 7, right? I'll do one more and then we're going to pause for a sec. How about 3 times 4 minus 2? 10. Okay, we could find the next two and there's nothing wrong with doing that. Or we could recognize there's a pattern that's developing between 1, 4, 7, and 10. What's the pattern? Plus 3. And it should make sense that it's plus 3 because there's the 3 multiplication at the beginning that's happening. So if you notice a pattern happening and you want to just finish the pattern, you could also do that. You wouldn't necessarily have to show the evaluation for it, okay? Everybody good so far? And what this says right here is that I'm supposed to take all of these and add them together. So whether you're doing it by hand in your head or with a calculator, I need to know what is 1 plus 4 plus 7 plus 10 plus 13 plus 16. What will we get if we add all of those together?
31.
How much?
31.
31. That sounds a little too small. 51? 51 maybe? Okay. 51 is correct. Okay, so that's fine if there's 6 terms, but if they told you to do this for 60 terms, that might not be your best friend, correct? I mean, you can create this list pretty quickly if there's just a few of them that you're doing, but the more that you're asked to do, the more cumbersome that process is. Agree? So it'd kind of be nice to have something that works a little bit more efficiently when we have more numbers we're trying to add together. And the way we're going to do that is that we're going to have some summation formulas. So these summation formulas specifically look at polynomial kind of powers, right? So we have a constant c. The first one is I, so it would be like adding 1, 2, 3, 4, 5, 6 together. So let me just write down a few of what these things are to sort of visually see what you're seeing. This is saying you're having c plus c plus c, right? A whole bunch of c's added together. This one down here is adding 1 plus 2 plus 3, right? That's what that says. This one here is saying I'm adding 1 squared plus 2 squared plus 3 squared and so on. And the last one is the cubes. Okay, does that make sense? That's what we're actually adding together in each of those. But again, the whole point is that I don't want to do it by hand. I don't want to figure out what is 1 cubed plus 2 cubed plus 3 cubed all the way up to 100 cubed. I don't want to do that. There's got to be a shortcut for it, and there is. So you don't have a whole lot of space the way that this is all structured. So I'm going to write mine on the right, but feel free to write yours sort of underneath what we just described as sort of what this is doing. There is a shortcut. Think about what happens if I added something together. In fact, I'm going to write down here that this is ending at c. N times. What is c plus c plus c plus c? N times. What's the shortcut way of doing that? C times n. So this one right here is a very nice one that you have seen before. It is just c times n. That's the formula. So if you're trying to add a constant, whatever that constant, that c can be anything you want. It could be 5, it could be 0.27, right? Any constant. And you're doing it from 1 up to n. You're just going to multiply it by how many terms you have. Because that one's a pretty straightforward one. The next one is actually very nice as well. All of them have variations of one another. But this one can be found very nicely. Let me actually show you how it's found sort of as an aside. You don't necessarily need to write this down. But if you take the numbers 1, 2, and I'm going to go up to 100 just because I need to stop somewhere. And I'm going to take that and then I'm going to flip them around and add them to themselves. 1. Then if I add all these together, I end up getting that they're all 101. Agreed? Now, why would I like to do that? Well, because I know how to add something together, 101 plus 101 plus 101, because they'll match. We just talked about how to do that on the first one, right? So this right here, there's 100 of these. We could have done n of these if we'd wanted. In fact, it might have been a little bit easier to see, but we're going to keep the number 100 since I've started it. So we would have the number 101 100 times, but I'd have to divide it by 2. Why? Why is this sum 101 times 100, but then it's divided by 2?
Because you added 2 of them together.
You betcha. I added 2 of them together. I doubled everything, right? I added them to themselves. So in general, what this is actually going to be is n times n plus 1 divided by 2. Because that n was acting like my number 100, right, that I just used. So I have n times n plus 1 divided by 2. I'm not going to show you the other ones, but this one was a nice enough one to show you pretty quickly. The others have forms much like this that if we manipulated them, we could find. The next one for n squared is n times n plus 1, but then it's times 2n plus 1, and it's divided by 6. And then the n cubed one is n squared times n plus 1 squared divided by 4. And each of these have names. If you've printed them out, they're already written on your paper, so I'll write them in for those of you who don't have this printed. This first one is called sum of constants. The second one is the sum, these are sort of descriptions, sum of the first n integers. The next one's called sum of squares. So this is sum of squares for the first n integers. What do you suppose the last one's called? Yeah, sum of cubes. It's the same thing we just did, but with cubes, right? So I have the sum of cubes for the first n integers. You don't need to necessarily know the names of those, but those are descriptions, like verbal descriptions of what we've written numerical descriptions for here, right? I mean, that's what these things over here are describing. A bunch of constants, a bunch of linear, like of integers squared and integers cubed. So how do we use this? Well, we use this kind of like what we do when we use limits. So we end up with something that looks like it's taken a bunch of these little pieces of things. Let's close this. Thank you. And we're going to break it apart so that it looks more like these pieces. Okay? So here's the way this works. We see an addition and subtraction right there. Agreed? Ours is a subtraction specifically. We can separate the subtraction out. So bear with me for a second. You might just want to write my final version of this. But I'm going to separate this out so I have it written like this. Okay, and the 1 and the 16 are still there, but this isn't my final version of it. And then the last thing I'm going to do is I'm going to take this 5 and I'm going to move it in front. Okay, so I can separate all of these pieces so that there's a 5 at the beginning. It's the summation from I equal 1 to 16 of the I minus the summation from I equal 1 to 16 of 4. Why? Well, I did that because these pieces now look exactly like one of these forms, but with a number placed in there for n, and there's a constant c that's given to us. It's a 4. But they look exactly like the forms on the previous slide or on your previous paper. So the 5 at the beginning is a constant multiplier, just like with limits, just like with derivatives, and just like with antiderivatives. With summations, constant multipliers come along for the ride. They don't affect the actual process. They just multiply the answer by, in this case, 5. Now, this says that I'm supposed to do the summation from I equal 1 to 16 of I. Which of these 4 summations is that matching? Number 2, right? I mean, that's number 2. And it says I should be taking whatever that n value is, right? That n is what's on top. And I can use this formula, right? This condensed formula to evaluate it. So my n over here is what? 16. So instead, I'm going to have a 16, and I have 16 plus 1, or 17, divided by 2. So instead of finding 16 different individual pieces, I can take this and I can multiply 16 times 17 divided by 2. And that will find for me the value of all of those 16 pieces added together. And then I've got to multiply it by the 5. Now, the second piece, which of the formulas will that one match?
First one.
The first one, right? It's just a constant. So it says I should take the constant, minus 4, and multiply it by n, which is my limit at the top, my upper bound. My upper bound was 16. So I'm going to take my constant, 4, and I'm going to multiply it by that upper bound, 16. Okay? Grab a calculator. Do some of that multiplication, subtraction, and so forth. What do you get? Okay, what was it? 6 what?
680 minus 64.
Okay, 680 minus 64. And if we subtract it, what will we get? 616. So as with everything, I do like to point out, what do you need to show me, like on a quiz, especially because we are going to take a quiz on Wednesday. What of this do you need to show me? Because in WebAssign, you don't have to show anything, right? In fact, you could do this the other way entirely and have never used summation rules at all, correct? I mean, you could do this. 16 is not an unbearable number to find 16 terms. It may not be pleasant, but it's not ridiculous. It's not 100 of them, right? So if I'm asked to use summation rules on a particular problem, what am I going to actually be doing on the paper? Well, everything that you write down here, you have to show the separation. You have to show the application of the formulas, and then you need to show the final answer down here. I don't know why there's a random red squiggly. We'll remove it. Those are the pieces that I want to see, and then I need to see. And the reason is because the first one, shows how I can separate it to be able to use the formulas. The second one shows that you're using the right formulas. So if you make a mistake, I can take off just a tiny bit because I know that you remembered the formula wrong, right? Instead of it being something else. And then the last one is just the arithmetic from your calculator, or if you did it by hand from doing it that way. But those are the three pieces that you would need to show. So one thing that sort of should be in your mind right now is before Wednesday, I need to know these four formulas because there's a quiz, right? And you do need to memorize these four formulas by Wednesday. There's some overlap between them, right? Some common pieces of them and so forth, but they are all different. Okay, let's try another one. This one is the summation from n equal 4 to 140 of n times n minus 1. There's three things maybe that I'm sort of looking at right now and thinking, well, that looks different than what I just did. Somebody tell me something that looks different.
N equals 4.
Ooh, the bottom says n equal 4, right? And in fact, that's a little bit problematic because all of these said I equal 1, right? So we're going to have to deal with the fact that this one's starting at 4 and not 1. Good. So that's one thing, and that's maybe the biggest problem. Not problem, but the biggest observation. What else do you observe? Here's a silly one. They're using n's instead of i's. Do you notice that? It doesn't really matter, but it is a little bit awkward because my formulas here are all in n, and n is something else in the left-hand side. That's a little awkward. Agreed? So if that happens on a problem inside of WebAssign, you can't do much about it. It's going to stay n because it's not going to let you change variables. But if you have one on a test or on a quiz and you don't like the letter that they're using, you can change it, and I have no problem with that. So we're going to actually change this so that we can make sure that we're not going to confuse the issue. And I'll make them i's, but you could make them something else if you wish. I will match what I'm doing most closely. So I'm going to call them i's. We're going to rewrite them with i's. There's one more thing that looks a little bit different on this one than the last one. So on this one, it's all added and subtracted with the variable inside, correct? But on this one, there's multiplication, right? It's I times I minus 1. So before we go any further, it would actually be very nice for us to distribute this and to rewrite it so that it will match my formulas a little more nicely. So it should say I squared minus I, and it will be able to be utilized more easily. Okay. Now, I really want to use the formulas, but this says that starts at 4. And the formulas only give me the answer if it were to start at 1. Right? So here's the trick. We change this, and we do make it start at 1. But when we do that, we've obviously made it bigger than it was before. At least, maybe I shouldn't say we've made it bigger, but we've made it different. Right? We expect that the value changed. That should say 140 on top, sorry. Because I now have 3 terms, namely A1, A2, and A3 that I didn't have before. Right? I put them in because I restarted my index on the bottom at 1 instead of at 4. So to compensate, I need to remove them as well. So the summation at the beginning will now include A1, A2, A3. So I subtract the A1, A2, A3 at the end. It's a balancing thing, like an equation, right? I added something, I subtracted something. It's like a fraction, top and bottom. If I multiply 2 on the top, I have to multiply 2 on the bottom, right? It's a balancing feature that we just did. But what it does is it allows me to come over here and use these formulas now, which is the goal. Because I don't know about you, but I really don't want to go up to 140 terms. 16, I mean, okay, maybe. 140, not a chance. Yeah? Not a chance. We're not doing it that way. So we're going to separate this out, just like we did on the last problem. We have I equal 1 to 140 of I squared minus the sum from I equal 1 to 140 of I minus A1, minus A2, and minus A3. All right. The first two are formulas that we have, right? Where my n value is what? 140, right? N is the number that's above. It's the upper limit of the summation. It's 140. So I squared is the first one, and I squared is the number 3 on here. It's n times n plus 1 times 2n plus 1 over 6. So this is the formula that we are going to be utilizing here. And my n is 140. So I'm going to have 140 times 141. And then I need 140 times 2. What else did it say? Plus 1. So it looks like that, right? And all of that is divided by what? 6 on this one. Yeah, 6. That's the I squared term. And then I'm supposed to subtract the I term. So the I one says I'm supposed to do n times n plus 1 over 2. That looks very similar to some of the pieces I already did. N is 140. N plus 1 is 141. But this one's over 2. And then how am I going to get A1, A2, A3? You just plug it in. So I'll write it up here separately. A1 means that I'm putting the number 1 into the formula. You can put it in the original one, or you can put it in the one that we distributed. Either way, I'm going to put mine in the distributed one. What is 1 squared minus 1? That one's actually 0, so if I had left that one out, it wouldn't have actually changed anything. The next one I don't think is, though. So we're going to do A2, which would be 2 squared minus 2, and that gives me what? That one's 2. And then on A3, I need 3 squared minus 3, and that one's 6. So I literally have minus 0, minus 2, minus 6 at the end to compensate for the fact that I included them when they shouldn't have been included from the original setup. Okay? Once again, please, if you wish, grab a calculator. We're going to multiply 140 times 141 times, well, it looks like 281 maybe, and divide by 6. We'll do the same thing with the 140 times 141 divided by 2. And in the end, we're going to end up subtracting an 8. If you show it in pieces, I have the ability to do more partial credit. If you want to show it all at once because you've done it on your calculator too, that's okay as well. Oh, I had it sitting over here. All right, these are large numbers, agreed? Did anybody get a value for the first one?
Yep.
What do you have, David?
9244090.
For the first one?
Yeah.
Okay, mine looks a little bit smaller than that.
924490.
That's what I have, yeah. 924490 is what I have. So double check on that one. Be careful with the parentheses on top. Sometimes it's a little messier to actually leave this written like this, and you might just want to change it to 281 instead. The next one, I have 140 times 141 divided by 2. What do you guys get?
9870.
9870. And then at the end, we have minus 6 and minus 2, so that's minus 8. That's not a good 8. Let's try one more time. Minus an 8 at the end. So take all those pieces, add, subtract them, so forth. I have 914,612. 914,612. Okay, so everybody has marked down something as a note to themselves to memorize these 4 formulas before next time, right? Okay, good deal. It'll be important. You won't be able to do the problem, especially if it ends up being a number that's like that, 140, without another option to do so. Okay, so what we're going to do next is we're going to connect, we're going to draw a picture of something that we're going to be then connecting to this idea. What we're going to be taking a look at, because you might have looked at this and said, okay, but We did a whole bunch of summation-y kind of things, but the title, Dr. Hand said that we were supposed to be looking at area, and I have yet to see anything about area. Okay, so this is the part where the area is going to come into play, and then we're going to connect it back to the summations we did. So this is going to be called the area of a plane region. So the area of this region can be approximated by using rectangles. And so when I talk about the area of the region, what I'm talking about, we're going to label this as A and this one as B. And we're talking about trying to find this arbitrary area. Not that the area is arbitrary, but the shape is arbitrary. Here. Okay, so if you remember back to the first day of class, one of the things that we talked about in first and second day was the fact that with pre-calculus, you can find area of very rigid shapes, like squares and rectangles, right? Triangles and circles even. Circles aren't even rigid, but they're very specifically defined. This is a generic curve. In fact, it doesn't even have an equation on this one. I'm just drawing a picture, right? And I want to be able to find the area of that shape that's shaded in. But what we want to do this, how we want to do this, is by doing it with something we already know, namely rectangles. So I'm going to erase my shading because I need to be able, you don't need to erase yours, it's okay, hold tight. I need to be able to show you what I mean by doing it with rectangles. So in general, what we're going to be doing is we're going to be subdividing this interval, and I'm going to subdivide it into 4 pieces because it's easy to draw. So this is sort of in half, and then I'm going to do it in halves again. Okay, and I'm going to create these vertical pieces that go up from here, kind of like I did on the A and the B. Now, obviously, those shapes are still not rectangles, agreed? They're not, but they're closer to a rectangle than the first shape was. Yeah? Okay. So if I could figure out sort of like the average height or use one of the heights along that curve, I could create a rectangle. For example, maybe I decide I want to use this as my height. And so I create a rectangle like this. Now, it's not a perfect rectangle. It overestimated it. But maybe I decide I want to use this as the height and I make this as the height. Well, that's not a perfect rectangle either. It somehow underestimates it. Or maybe instead of using either of those, I use sort of the point that's halfway in between right here. Right, the midpoint, and I say, let's use that one. Well, it overestimated a little, it underestimated a little. That might be my best option on that particular rectangle, but it's still probably not perfect. Okay, is everybody with me? So we are going to use those 3 ways of doing it. We're going to looking at the left-hand endpoint, the right-hand endpoint, and the midpoint. But imagine now, if you subdivided this further, what if the rectangles now were half as big as they were before? And what if you subdivided that again? And you end up with infinitely many little rectangles showing up. And you keep subdividing, you keep subdividing, you keep subdividing. The shapes start to look more and more like rectangles as you go, don't they? They're still not rectangles, but they're getting closer. So your overestimates and your underestimates, no matter whether you picked the left point, the right point, or the midpoint, are getting better. The more rectangles, the better the approximation. So there's 3 ways we're going to do it, as mentioned. We're going to use left endpoints, right endpoints, and midpoints. So we're going to start here on this one with left endpoints. So go ahead and take this image. That's why I didn't really need you to do this, because you're going to flip over to the next page. So if you flip to the next page, we're going to draw in rectangles. And we are going to do them with 4 rectangles just because the drawing's pretty manageable, not because there's anything special about the number 4, okay? So we're going to cut it in half, and then we're going to cut those in half again to create 4 different approximately equal width. Our goal was that they would be equal width sections. So this one is A, and this one is B, whatever those endpoints are they give to us. And with left endpoints, it means I use the leftmost point of the region. So if I'm going with this particular first rectangle, or rectangular-ish shape, you use the left point, which is the point at A, and you draw it straight over, and you create a rectangle down from here. And we definitely get an overestimate, right? But if I use the second rectangle and I do it over it, now I get a much bigger overestimate, so that's not cool at all. But on the third one, now I've got an underestimate. And on the fourth one, I also have an underestimate. So the shape that I'm getting in here is actually not as far off as you might have guessed. The first one's an overestimate. Hang on, let me make that a little bit thinner of a shader, highlighter. So this one's an overestimate and this one's an overestimate, but it's almost like they balance out because this one's an under and this one's an under, right? So this particular curve might be very well served actually to use left-hand endpoints because some overestimate, some underestimate, and we have this sort of a balancing feature going on. Now that's good because that's happening, I should say, because of this particular kind of curve. If the curve hadn't done this, that might all be overestimates or they might all be underestimates, but this one wasn't. So what we're going to do is we're going to call each of these interval, like hash marks, a value. So this is going to be called x0. This one's x1, x2, x3, and I'm ending at x4 because I have 4 rectangles. If I had more rectangles, I would have more subscripts. And you start to see some subscript notation like we just used, right? Back with those a sub i's. It's coming into play. So how do I find the area of a rectangle? Yes, so the area of a rectangle is either base times height, or you can think of it as length times width if you prefer. Everybody good with that? Okay, so let's talk about what the bases and the heights are of these rectangles. Well, if I've subdivided it properly, all the bases are the same, correct? Right? If I divided it evenly, perfectly, then this length right here is the same as this length right here, and the same here, and the same here. Of course, my picture's not perfect, but you can pretend for a minute like it is, right? Sure. Okay, so all of those are supposed to be the same. And we're going to give them a name. The name we're going to give them is actually going to be, sorry about that, delta x. That's not a good delta even. Delta x, it looks like a triangle. It's just width. It's the change in x. That's going to be the width. And they all have the same width. Now, they all have different heights, though, correct? Or at least potentially different heights. Some of them might actually coincide depending on the curve and so forth, but they have potentially different heights. The first height is actually right here. And so this height is actually the y value for that particular x value. So it's actually f of x sub 0 because the x value we've relabeled as x0. So x0 gives me the x value. The corresponding y value is f of x0. So what happens when I go to the height of this next one? Well, it's over here somewhere, and it's going to be f of x1, right? This height's f of x1. So to avoid having to keep drawing it, listing it over, what's this height going to be? Yeah, f of x2. And what's this height going to be? F of x3. And I do not need f of x4. How come? There's a couple different things you could say here that would sort of make it.
We're going off the left end.
We're going off the left endpoints. The left endpoints start at 0 and they end at 3. Does that make sense? So when we go to right endpoints, it's going to be different. We are going to use x4. But on these, it's going to start at x0 and end at x3. So I'm finding areas. So like we said, area of the rectangle is going to actually be the length times the width. So my length, or my height and base, whatever, what do we do? Base times height. The base is delta x, and the first height is f of x0. And then I have another delta x, because that's the second one's base, and I have a height of f of x1. And then I have the next one's base, which is delta x, and I have the height of f of x2. And finally, I have the third one's base, delta x, and the height of f of x3. Okay, does that make sense? I'm just finding 4 different areas of rectangles and I'm adding them together. But what do all 4 of those have in common?
They're the same equation.
Like more specifically, what do they have in common? Like very, very specifically, they have something in common. The delta x. They all have delta x in them, right? They're all found the same way. They are all the same equation, but very specifically, they all say delta x. So I can actually do something called factoring, like algebra factoring, right? Where I pull the delta x out and I say, okie dokie, well, I'm really just, if I factor out the x, adding f of x0 plus f of x1 plus f of x2 plus f of x3. So I don't need to do 4 multiplications. I need to do 1 addition of 4 terms, and then 1 multiplication. But what's in parentheses with all those f sub x's can be condensed. And we can actually write that as delta x times the summation on this one from I equals 0. Good grief. Move that down. I equals 0 to 3 of f of x sub I. Right? It's a bunch of f of x sub i's added together, starting at 0, ending in 3, and they all get multiplied by delta x when we're done. All right, let me show you what happens with the right end point. And then midpoint we don't do quite so specifically. That was weird. So for right end point, we draw the same 4 rectangles we had before. At least approximately, so we try. But as mentioned, we're going to use the right-hand endpoint instead of the left-hand endpoint. So on the first rectangle, this is the height. It's not a very straight height, but pretend. On the second rectangle, this is the height. The third rectangle, this is the height. And the fourth rectangle, this is the height. Now again, because of the curve, it kind of looks like it balances overestimates, underestimates, and it very well may. And I'm finding these areas. My labels start the same way. This is x0, x1, x2, x3, and x4. But my heights are now determined by the right-hand endpoint instead of the left-hand endpoint. So yes, there is a delta x, but I actually have f of x1, f of x2, x3, and x4. And I can rewrite this in that summation notation as that the delta x times the summation from this one starts at 1 and goes to 4 of f of x sub I. Because I'm using the right-hand endpoints instead of the left-hand endpoints. So I start at x1 and end at x4. Okay, so I can draw the picture, but there's no nice, beautiful way of writing midpoints. So we can draw the picture. We'll start with the picture the same way we did before. Approximately split my interval into 4 pieces. But what we're going to do is we're going to split and find the midpoint height for each of these. So in some sense, the midpoint location's height is going to be my height here. Now I know that makes it look like I've just created 8 rectangles. That's not my purpose in doing so. I'm actually just using those dotted lines to represent where I'm finding my point up here for my height. So that's my height value. Like this. And my areas, again, seem like they're balancing things as well from the overestimates and the underestimates. But there's not a good way, like we had down here, you may not think that's a good way, but there's not a way to write anything like that in a closed form here. We can still do it, there's just not a condensed way of writing it. Okay? So let's do an example and finish this up. We're going to use left endpoints, right endpoints, and midpoints. We're actually given a curve this time, and we're going to try and find these approximations. Okay? So if you take a look at this one, it's not a bad idea to sketch this graph to start with. The graph is the graph of a parabola. The parabola is shifted up 5. That's the plus 5 at the end. But I only want the right-hand side. I mean, you can draw in the left if you wish. That's terrible, but I only want it to go from 0 to 4, 0 to 2. That's what it said, 0 to 2. So it's starting here at 0, and I'm going over here. I'm trying to make it look a little bit exaggerated to try and get our sketch in here nicely, too. So my image is actually that I'm trying to find this area right here. Okay, can everybody picture that okay? That's what I'm looking for. Now, do you have to draw this picture? No, you don't. But what probably would be helpful is to at least draw a number line. So your number line is going to start at 0, and it's going to go to 2. And you need 4 rectangles, which means you need to divide it in half. So what is the mark I just put? What x value is that? It's 1. And I need to divide it in half again in order to get 4 rectangles. And they're not always 4. You could have 6 rectangles or 8 rectangles. But what are those hash marks representing? Yeah, half and 3 halves. So you can put like 0.5s, or you can put the fraction 1/2, your choice. I'm kind of do either one. It just depends on what mood I'm in. I'm in a decimal mood apparently right now, so we're going to do decimals. So I got a 0.5 and I got a 1.5. All right, so we're going to start with left-hand endpoints, and I'm going to abbreviate it as L of x for the left-hand side. What's the width of every single rectangle I'm going to draw? Like if I literally drew all of these in here, what's the width of all of them? 0.5, right? It's the distance right here. How far does it go from there to there? It's 0.5. And then I need to have 4 rectangle heights. But the 4 rectangles are being determined by the left-hand endpoint. And what is the first left-hand endpoint? It's a 0. So the first left-hand endpoint is going to be f of 0. And then I'm going to have f of 0.5. And then f of 1 and f of 1.5. There are 4 heights there. Those are the 4 left-hand endpoints, and I'm finished. Now let me just write down really quickly the right-hand endpoints notation and then the midpoint. And then we'll go back and we'll do the calculations all at the same time. Okay, so for the right-hand and the midpoint, there's still widths of 0.5. It doesn't matter where I'm measuring the height from. The widths of all the rectangles are the same. And I'm going to have 4 heights. Where will my first height, or what approximation value am I going to use for my first height with right-hand endpoints?
2.
If you want to start at 2, you can, or you can start at 0.5. So if you want to start at 2, more power to you. We'll start at 2 since I heard that one first. So we're going to start over here at 2, and then we're going to do what? 1.5, and then 1. Whoops, sorry. And then we're going to do 0.5. So those are the 4 of them if I go from the right-hand side over to the left, or you can flip the order around. What if I'm doing midpoints? What is the midpoint x value? We'll do the very first one here, right here. What is that midpoint going to be? 0.25, right? Think about money, right? A quarter. 0.25. So this is f of 0.25. What would the next one be? You have to work harder for the midpoint ones. What's this one? 0.75. What's the third one? Good grief. 1.25. And what's the fourth one? Good. 1.25 and 1.75. Whoops. I'm trying to get this to erase. Hang on. Patience. Cut and delete. Okay, here's what you can do. You can use your calculator to do this. So let me shoot it with you really quick. This is the last thing we're going to do. Grab your calculator, put the original equation into y1. So it's 2x squared plus 5. Okay, y1 says 2x squared plus 5. Now, I mean, you can figure out what the 0 is and what the 0.5 is and the 1 is and the 1.5. You can find all of those values, and you can actually number crunch and do a lot of that by hand. What I've shown on the board is exactly the minimum of what I want you to write down, because your calculator can do all the rest of this for you, which is pretty cool. Here's the way that you do this. In the regular screen, so go back out to your regular screen. I want you to hit the vars button. It says vars, and go over to yvars, function and y1, and then put a parenthesis 0. Don't hit enter. It should just say y1 of 0. So right now, if you're doing this in your calculator, this part is the part you're doing, and it says y1 of 0. Does everybody say that? Did you find it? Joshua, you find it? Hayden, can you help me? Yep, there you go. Okay, everybody else find it?
What do you click once you get into y bars?
Y-bars, function, y1. And then press 0. Okay, before you hit enter, hit plus. And we're going to do it again. Did you get stuck? Yeah, that's fine. Press enter. You're good. And then put parenthesis, 0, close your parenthesis, plus. And do it again. Vars, y-vars, function y1 of 0.5. Plus vars, y-vars, function y1 of 1 plus bars, y bars function y1 of 1.5. Press enter. You should get 27. Did you get 27? And then you're going to multiply it by the 0.5 at the front. So all of this here was 27. And then it gets to be multiplied by 0.5. Your answer ends up giving you 13.5. The other two are very similar. I'm going to fill those in for us and have it posted. But you're using the calculator to find it. If you don't like what we just did, then you can type them all in. It's not going to hurt anything. It's just going to take a little bit longer, okay? I'll see you guys all on Wednesday. Okay, so, and the nice thing is that if we've actually done all this in our calculator and we've typed in the y1 of 0, y1 of 5, all that kind of stuff, we could actually use that and not have to type it all back in again exactly for the next one. Because the only thing that's different between this first one that we just did with the left-hand endpoints and the right-hand endpoints is that we need to take this one out and we need to put this one in, right? Everything else matches, 0.5, 0.5, 1, 1, 1.5, 1.5. The only difference is the f of 0 and the f of 2. So in your calculator, if you hit second, enter, it pulls up the previous entry. And if you do it again, second, enter again, it pulls up the entry before that. And you can actually type backward, like arrow over and change the y1 of 0 to say y1 of 2. And if you do that, it will tell you that this value here is actually a 35. And so then you have the 0.5 that gets multiplied by the 35, and you get 17.5 for the right-hand endpoints. So 13.5 on the left-hand endpoints, 17.5 on the right-hand endpoints. We can do second enter for the next one as well. It's not really quite as helpful just because we end up with having to change so many things. So if you wanted to just enter it again by hand, you could do that. But if you add these in and you do y1 of 0.25 plus y1 of 0.75 plus y1 of 1.25 plus y1 of 1.75, if you put all of that in and you calculate that, you're going to get 30.5. So all of this is going to be 30.5, and you multiply that one by the 0.5 at the beginning, and you're going to get 15.25. And it's reasonable that the midpoint, generally speaking, is between the left-hand endpoint value estimation and the right-hand endpoint value estimation.